Okay, thank you. And this is work with the Wei Run Wang and Jalei Wang, no relation. Wei Run was supposed to give this talk, but again could not make it due to visa issues, so I'm giving this short talk instead of him. So what I'm going to be talking about, it's kind of two things. The first thing I'll talk about is actually the mini-batch procs, which I'll present in a bit. So the mini-batch procs is you can think of it as a very convenient building block with a very simple analysis for stochastic optimization, and then we'll see how to use the mini-batch procs in order to reduce memory requirements for distributed optimization. So let's start with the mini-batch procs. So what we're dealing with is the standard stochastic optimization problem. We want to minimize some stochastic projection with respect to W based on samples of Z. And we know how to do that optimally, statistically, and computationally using stochastic gradient descent. So in stochastic gradient descent, in each iteration, we get a sample and we update W based on it. And we update W based on linearization of an objective around our current W based on a new sample. So we all know this by heart. The problem, of course, is this is very sequential. And so instead of working with one example at a time, we can work with mini-batches and perform mini-batch stochastic gradient descent. So mini-batch stochastic gradient descent, we collect a bunch of samples and then calculate the gradients for all of them and then update W and then collect another batch. Another way to think about it is that each time we linearize the objective with respect to each one of these, we're actually linearizing based on a kind of stale iterate because we're not using the latest. In order to calculate the gradient for Z3, we're calculating the gradient in the location that doesn't take into account Z1 or Z2. Right? So our iterates are always stale, and so mini-batch stochastic gradient descent is somewhat inherently worse than stochastic gradient descent. The best you can do is always use a mini-batch size of 1. The larger the mini-batch, you have deterioration, and you can analyze this based on smoothness and show that you're bound to deterioration and say that if the mini-batch size is not too large, the deterioration is not going to be too bad. But it's definitely the case that the larger the mini-batch, the worse. Okay, so this is mini-batch stochastic gradient descent. Mini-batch procs performs the following update. There is no linearization. So what we do at each iteration, we collect B example. B is the size of the mini-batch. And then we optimize our objective, our sort of empirical estimate of the objective based on all examples in the mini-batch, plus a regularization term that says we're not going to get too far, a prox term that says we're not going to go too far from our previous iterate. Okay? So again, the difference versus mini-batch stochastic gradient descent is that in stochastic gradient descent we'll only look at the gradients of f. We'll look at the linearization of f. Here we're minimizing f itself. Okay? So this is similar for mini-batch size of 1. This is exactly the passive-aggressive algorithm, and this is similar to what Manfred talked about. How do you call this, Manfred? I remember implicit updates, where you're doing each update not based on the gradient in the current iterate, but based on you're updating to a new location based on the gradient in the new location. Okay, so this is definitely more powerful for stochastic gradient descent. With one iterate, then this is just passive-aggressive, and passive-aggressive is not really that much better than stochastic gradient descent. But when you go to larger batch sizes, unlike mini-batch stochastic gradient descent, which gets worse as the mini-batch sizes gets bigger, here we'd expect things to get better as the mini-batch size increases. Because when I have a mini-batch size of 4, not only am I not stale, but I'm optimizing here over 4 things together instead of just optimizing over each one separately. Okay? So we expect to not see a deterioration, and in fact we do not see a deterioration, so you can prove that no matter what the mini-batch size is, you get the same statistical guarantee you'd get based on BT examples that you have overall as if you're doing stochastic gradient descent or ERM or the optimal statistical rate. So there's no deterioration with B. You can use as large B as you want to. And there's been previous analysis of this exact same algorithm dependent on all kinds of quantities. Smoothness, other quantities had additional terms. We don't have any additional terms, no dependence on smoothness or anything, which is necessary, for example, for analyzing stochastic gradient descent. So mini-batch stochastic gradient descent, for example, has this additional term. This is where things deteriorate as the mini-batch size increases and depends on smoothness. You do not have that if you solve the exact prox problem. And you can get extensions for this to all types of, any setting you can think of, smooth, strongly convex, non-strongly convex, non-smooth, whatever you want. And it's going to be important applications. Also, you don't have to solve this exactly. You can solve this only approximately, and don't try to follow the slide now. But the point is that you only have to solve it to a reasonable extent, and things still work. Okay, just slight iteration of constants. Okay, so how is this useful? Okay. It seems not very useful because at each iteration we have to solve an entire optimization problem. Kind of what's the point? I mean, using larger mini batches, I mean, I have to solve more and more complicated mini batches, and I don't really get any improvement when I get larger mini batches, or at least not in the bound. So one way we'll show this is useful is reducing memory requirements for distributed optimization. So in distributed optimization, we have the same optimization problem, but now we have n machines, and each machine receives samples from the source distribution. And what we'd want to do is use all these machines to reduce our computational cost. So ideally, we want something that has linear reduction in computational cost, okay? And also doesn't use too much memory and doesn't use too much communication. So how can you do that? So in some sense, the best way we know to do that is using mini-batch stochastic gradient descent, or better yet, accelerated mini-batch stochastic gradient descent. So you're processing each mini-batch on parallel on all the machines. And this does, in fact, have a linear reduction in runtime. The problem is that you have to communicate, well, I don't know if you consider this a lot or not a lot. If you have n samples, you have to communicate n to the 1/4 times, and for the 1/4 examples. So polynomial, you do have a polynomial reduction communication, but it's still a polynomial amount of computation. Polynomial amount of, communication. You can do much better in terms of communication with, for example, distributed SVRG, which I'm not going to go into here. You can basically distribute SVRG, perform the batch calculations on all the machines, and stochastic on one machine. The point here is here you have to store them, you have to go several times, a few times, but several times on the entire data set. And so even though you get very good communication cost, you actually have to store all the data on all the machines. So how can you use the mini-batch procs to reduce that? So what you do is you can have an outer loop which executes mini-batch procs. So you take, for example, the first mini-batch across all the machines. You solve the procs problem on this mini-batch using distributed SVRG. Then you go to the second batch, solve the procs problem using DSVRG, and so forth. If you crunch all the suboptimalities of the problems, you can see that you don't get any change in computational performance. So the computational performance doesn't change, the statistical performance doesn't change as you vary the batch size. What does change is changing the batch size gives you a trade-off between memory and communication. Okay? For a larger batch, you need more memory because you have to store the entire batch in memory on each of the machines. But you only have to communicate a few times for each batch. With a smaller batch size, over here, you'd get less memory, but you'd have to communicate more because you have to communicate several times for each batch. So that's all. And I want to again emphasize the mini-batch procs. It's pretty obvious, maybe thing in retrospect. It's a very useful procedure. I think also in other things, this is just one example for distributed optimization where we can leverage it. Thank you.
Yes, questions?
For distributed optimization? No. So that's an excellent question. I decided in this talk to talk more about the mini-batch procs. Distributed optimization, I can give. Can I get another 50 minutes maybe? And, okay. So in fact, I've given complete talks on distributed optimization. We have no inherent limits. For all we know, it's possible. Might be possible. This ideal solution might be possible. It might be possible to do distributed optimization with constant memory, near constant, or maybe logarithmic amount of. I should say there's log factors missing in all of this, but logarithmic amount of communication and linear speedup. So it's completely open.
Maybe I missed this. How do you compute the implicit update?
For the distributed optimization, using distributed SVRG, which I did not describe. So take it, we have a method that does distributed optimization well, but requires storing the entire data set. It's not a...
Okay, let's thank Nati again.